Do you feel overwhelmed by all the things you think you need to study in order to feel prepared for your next technical interviewer? You are not alone. Some software engineers spin their wheels by spending time studying concepts that don't appear frequently in interviews. Other engineers put off applying for jobs altogether until they feel they know how to code every data structure, every sorting algorithm, and every searching algorithm. The secret to success in technical interviewing, though, is to understand concepts well and to be able to sensibly implement them rather than memorize code for every single one. In this course, I hope you focus your preparation strategy by sharing a mix of personal qualities, specific communication skills, and computer science knowledge that most interviewers are looking for. In addition to your technical skills, which we'll get to very soon, there are some personal qualities your interviewers are going to be looking for to try to figure out if you're going to be a good addition to the team. The qualities I believe are most important to demonstrate to your interviewers are emotional intelligence, intellectual maturity, curiosity, perseverance, and confidence. Let's talk more in depth about each of these. Emotional intelligence is your ability to respond appropriately to questions, engage in meaningful conversations, feel empathy, and show kindness. A very small example would be welcoming someone back to the office after they had been out sick for a week and asking how they're doing. Emotional intelligence is very important in a well-functioning team. Intellectual maturity appears when you ask meaningful questions, when you seek to understand problems or perspectives, and when you can adequately articulate your thought process to your colleagues. Intellectual maturity is really important, especially for software engineers who spend a lot of their time asking questions to better understand problems. I think most of us know what curiosity is. It's a desire to know more. Maybe a desire to understand how something works, or the desire to explore something new. Curiosity is a valued trait among engineers because it's the precursor to innovation, and because software engineers are almost always working on products that really push society forward, curiosity is hugely important. Perseverance is another one I think most people already understand. It's the ability to stick with something even when it's difficult and to see it through to completion. You've probably experienced yourself how important this is for software engineers. Without it, we'd walk away from bugs in our code all the time and just leave them sitting there. Last but not least on my list is confidence. People want to work with other people who know what they're doing or who have the self-belief to know that they could figure things out. When you interview from a place of strength and capability, it shines through as confidence, and it's awesome. Remember, your interpersonal skills are just as important as your technical skills, and all of your interviewers are going to be looking for these too. I want to touch on some non-technical skills before we dive into the Python material. The non-technical skills I believe are most important to demonstrate to your interviewers are your problem-solving ability, your ability to ask good questions, your ability to understand your own assumptions about a problem, your ability to understand constraints, and your ability to collaborate. Let's talk more in depth about each of these. Problem-solving ability is an umbrella term you hear a lot in the tech industry. Given that software engineers need to figure out how to do things with code for a living, being able to solve problems is really important. Generally, what people mean when they say they want to hire someone who is a good problem solver is that they want to hire someone who can use what they already know, whether they obtain that through school, reading, or experience, to accomplish something specific in the workplace that may not be well defined. One way to demonstrate your problem-solving ability, or to try to get better at solving problems, is to start by asking good questions about the problem itself. This brings us to our second point, which is asking good questions. Good questions have a number of qualities. They should be specific. They should let the person you're asking know what you already know, so that the other person can build on top of that. And good questions should also be asked of the right person. For me, this means the person who can answer my question the best, who is also the least busy. Sometimes the process of asking questions to try to better understand a problem uncovers some unconscious assumptions you are making about the problem itself. Understanding your assumptions is a really important skill because if you're unaware that you're bringing biases or expectations into a solution, the solution may wind up not solving the problem or doing the task effectively. And similarly to understanding your assumptions, the skill of identifying and understanding constraints of a problem is also something engineering managers are looking for in their teammates. A team whose engineers know what their boundaries and limitations are won't spend time trying to come up with solutions that aren't feasible or that are ineffective. In the end, this saves everyone time, and time is money. The last non-technical skill on my list is collaboration. This is another word I see used a lot in job ads, and I hear engineers say all the time that they love collaborating with their team. Collaboration may be something you're innately good at, or not, but it is a skill you can develop. If you're a good collaborator, it means you're skilled at both listening to others' ideas and questions and sharing your own ideas and questions. It means you work with a partner or a group effectively toward a shared goal, and that you do so with respect even if you disagree. Remember, your interpersonal skills are just as important as your technical skills, and the people with whom you're interviewing are going to be looking for both. We spent some time talking about what personal qualities your interviewers are probably looking for. Now, let's shift to focusing on how you can use Python to demonstrate your knowledge of computer science concepts and software engineering. We'll start with collections, which are things like tuples, lists, dictionaries, and sets. Collections are a fundamental way to store and organize your data. Since collections form the basis of so many coding challenges, you should be able to compare and contrast them readily, and it would be really helpful if you had several built-in methods memorized for each data type. If you can understand the runtimes of those built-in methods, even better. Let's take a quick look at each collection type, starting with tuples. The syntax for tuples looks like this. Tuples are immutable, meaning you can't change the data inside them once you create them. They're ordered and also iterable, so you can loop over them and index into them constant time. Because of these characteristics, tuples are a great data type to use when you want to store data that you don't want to be changed later. Be sure you know how to index into a tuple and find the length of a tuple. A couple other handy built-in methods are count and index. Lists are very similar to tuples in that they store an ordered collection of items with syntax like this. They are mutable, meaning you can change the data inside them, and they're also ordered. You can iterate over a list in linear time. The mutability of lists makes them a good choice when you want to store data that may need to change later. In addition to indexing into a list and finding its length, some built-in methods you'll want to have in your mind are append and insert, which help you get items into a list, pop and remove, which help you get items out of a list, and the reverse and sort methods are also really handy during coding challenges. Now, unlike tuples and lists, which store data in a linear sequence, dictionaries store data in key-value pairs with syntax like this. Dictionaries are mutable, just like lists, and you can iterate over a dictionary's keys, values, or key-value pairs. This makes them a great data type choice in coding challenges that require you to keep track of several pieces of related information at once, like the example here, where we have some quantity, in this case 5, related to some thing, in this case cupcakes. Up until Python 3.7, dictionaries did not preserve order. However, as of Python 3.7, dictionaries do store their key-value pairs in the order in which new keys were added to the dictionary. This is another really powerful new feature about dictionaries. Dictionaries are incredibly powerful collections and appear frequently in coding challenges. You'll definitely need to know how to access values in a dictionary by specifying their keys like this. You'll also want to know the keys, values, and items method that allow you to access keys, values, and key-value pairs, respectively. If you need to remove a key-value pair from a dictionary, you can do that with the pop method or with the del keyword, which stands for delete. Last but not least are sets. Sets are really cool. They are super fast and mutable like dictionaries, but they only hold unique values, not key-value pairs. You can think of them kind of like a combination between lists and dictionaries. Sets are mutable, so you can change the data that's in them once you've created them, but they're unordered, meaning you can't index into them. You can iterate over sets in constant time too, but they aren't ordered. All of these characteristics make sets a good choice of data type to use if you're working on a problem that involves unique data and large data sets. Some useful built-in methods for sets are things like add and update, and remove, which all of these allow you to alter what's in the set. And since sets in Python are also representative of mathematical sets, you can call methods like intersection and difference to compare and contrast two sets. Knowing these collections well will save you time in interviews because you won't have to create the built-in methods from scratch, or stand there wondering how to work with the info you've been given in a coding challenge. One of the first topics we should talk about is time complexity, because time complexity comes up in just about every technical interview you'll do. Time complexity describes the amount of time it takes to run an algorithm in the worst-case scenario compared to the length of the input. Time complexity can be affected by hardware and the operating system, but we always ignore that when we talk about time complexity. You've probably seen a graph something like this, and this graph is showing you a comparison of the various kinds of time complexity. The closer the line is to the x-axis, the better the runtime. This is important because we always want our programs to run as fast as possible. In this graph, which has a logarithmic scale, you can see that the red line, which represents O log n, is just about right on the x-axis. The green line, which is linear time, is right above that, and then O of n log n and O of 1. Time matters, especially at scale, and your interviewers are going to be checking to see if you really understand this. Let's walk through a couple examples of some of the more common runtimes. Here is O of 1, or constant time. Here, we have a simple variable called myFavoriteDesserts, which is bound to a dictionary that has a couple key value pairs. We could print one of those values by accessing its key, and this would be done in constant time. Many simple checks and variable assignments like this are always constant time. Another example is linear time, which is called O of n. Here, we have a list called myFavoriteDesserts that has a couple items in it, and we're going to loop through that list. So for every string in the list, we'll simply print the string. Simple for loops are almost always O of n time because we have to visit every item in the list or the tuple that we're looping over. Next, we have O log n. A very, very popular example of O of log n is binary search, because in the worst case of binary search, each time you eliminate options, you eliminate half of them. I do want to point out here that the base is 2. The next runtime we'll talk about is O of n squared. Here's a slightly more complex example. We have that same variable before, the list called myFavoriteDesserts, and we also have a second list called quantities, which has some integers in it. In the code below, I'm looping through the dessert list and the quantity list, and I'm printing the item from each of those. Since we have 2 for loops and one is nested under the other, we have to run through every item in the dessert list and every item in the quantity list. This creates a runtime of O of n squared. There are a few other runtimes, O of n log n, O of 2n, and O of n factorial, which pop up from time to time in coding challenges, although they don't appear as frequently as the others I just showed you. Again, it's really important to understand runtime because your interviewers will ask you at the end of your interview or when you've come up with a solution to a coding challenge. I showed very small examples of how to find time complexity. But how do you calculate the time complexity of a solution if there are 2 or more time complexities in the steps of that solution? It's pretty simple. The time complexity will just be the worst one that's present in the solution. The reason is that we always want to know about the worst-case runtime. Our next topic is recursion, which unfortunately some people put off studying for their technical interviews, but recursion does come up fairly frequently in coding challenges, so I really encourage you to dig in here. What is recursion? Recursion is an elegant method of solving a problem where the solution depends on solutions to smaller occurrences of that same problem. This means that a function is going to be calling itself, and I'll explain and show you more in just a second. Here's how we approach recursion. We first need to divide a problem into smaller subproblems. The key here is that those smaller subproblems must be the same type as the original problem. We can solve those smaller problems and then combine the results from those to solve the original problem. When we think about solutions to recursive problems, there's a few components we need to keep in mind. The first is called the base case or the degenerate case. Basically, this means, how do I know when I'm done recursing? How does a function know when it should stop continuing to call itself? The base case is whatever is sort of the lowest common denominator or the smallest slice of the problem that gets treated differently. In addition to the base case, we also need to make progress. So every time the function calls itself, we need to slightly tweak the thing that is being passed in as the argument. And this progress, as we call it, continues to reduce the problem until we reach the base case. I'll show you an example. So here we have a function called getListLength, and we're passing in a list as an argument. Our base case is the condition where the list is equal to an empty list, or the argument is equal to an empty list. In that case, we're going to return 0 because the length of an empty list is 0. On the last line, you can see we're returning the value 1 plus a function call. So here's where we see the function call inside of the function call. And here, when we call the getListLength function, we're passing in my list again, but the progress portion comes with the fact that we're indexing, or rather slicing, my list from the first element to the end, and we're omitting the 0th element. And so doing this allows us to constantly slice that list smaller and smaller and smaller each time we recursively call the function. And because we consistently slice the list smaller and smaller and smaller during each function call, we eventually get to our base case, which is the case where my list is equivalent to an empty list. Once we hit that base case, we return 0. Once you return a value from the base case, all of the returned values that happened from previous function calls get combined one on top of another until eventually you're returned with the value that solves the original problem. Al Swigart, who attended and spoke at PyBay in 2018, did a really great talk explaining recursion, and I highly encourage you to check it out. He does a really great job explaining what recursion is and goes into a lot more depth about recursion. I really encourage you to not be afraid of recursion. It truly is an elegant way of solving problems, and your interviewers will be impressed if you're able to work it into one of your solutions. If you're preparing to interview for your first software engineering role, or if you haven't interviewed in a while, you may not be familiar with the steps in the technical interview process. In this chapter, I'll share what to expect at each stage. The interview sequence almost always starts with a 30-minute call with a recruiter. You'll be asked the usual phone screen questions, such as why you're looking for a new job, what languages and frameworks you know, what you've been working on lately, and so forth. If that goes well, you'll be asked to schedule a 30 to 60-minute technical phone screen with an engineer. This usually involves sharing your screen or using a web-based code editor and doing some live coding with the interviewer. Live coding is the process of using a web-based text editor or a command line tool so you can demonstrate your problem-solving and coding abilities to your interviewer. If the technical phone screen goes well, you'll probably receive some kind of programming assignment or assessment to complete at home and submit within a week or so. A take-home assessment is a self-contained project that's designed to take you several hours or several days, depending on the employer, to complete. The purpose of a take-home assessment is to give you time and space to demonstrate your best work. If the hiring manager likes what you submitted, you'll be asked to come in for an on-site interview. These usually last at least a few hours, and you'll likely meet with several different people. During an on-site interview is when you'll do whiteboarding or pair programming. Some people get really nervous about whiteboarding, but whiteboarding is simply the process of using a whiteboard or a piece of paper to address a coding challenge. This allows you to demonstrate your problem-solving abilities and your coding abilities at the same time. Pair programming is very similar to whiteboarding, but you're collaboratively solving a problem with another person using code on your laptop, whether in person or remotely. There are a variety of ways and opportunities to show your skills throughout this whole process. Interviewing is a skill, and you can get better at it if you practice, just like any other skill. Object-oriented programming is a very large component of almost all technical interviews where you would be using Python. The reason is that classes and objects are everywhere in production code, and so hiring managers will be looking to make sure that you know how to write them. You've probably seen the syntax and structure for a class before. We use the class keyword and we name the class with a capital letter, and then we provide some attributes and maybe some methods, including the init method, to the class. We can instantiate the class by calling it and passing in any arguments that are needed. Here in this example, we have to pass in the name of the dog. We can access the attribute species by saying toby.species, and that will return to us the value that is stored in the species attribute. Finally, we can say toby.name, and this will return to us the name that we originally passed in when we instantiated the dog object. Here's the class attribute, and here's the instance attribute. The class attribute will get passed along to any instance of the dog class, but the instance attribute is always unique to that particular instance that you created. We can also define instance methods. Here we have a method called greet, and in this method we're simply printing the dog's name. So after we instantiate our dog object called Toby, we can say toby.greet, and it will print for us this string that says, "Hi, I'm Toby." Why are objects so useful? There are three main reasons. One is encapsulation, another is inheritance, and finally we have polymorphism. Let's talk about what each of these means. We'll start with encapsulation. Encapsulation is the idea that the data and functions associated with an object are contained together within the object. This keeps them safe from outside interference. We can go back to our dog example to illustrate this. So we have species, which is canine, and the greet method. Species is the data and greet is the function, and all of this is stored inside of the dog class. The second concept of object-oriented programming is inheritance. Inheritance allows classes to be arranged in a hierarchical order. For example, we could start with a canine class, which is a parent class, and then a dog class that is a subclass of canine. We could go even further still and create a class called terrier, which would first inherit from dog and then from canine. And you can see from these examples that we could do other variations as well, like coyote or foxes. Here's a class called mammal, which we're going to use as a parent class. You can see we have an attribute called blood temp and a method called identify, which prints the string, "I'm a mammal." Next, we can create a dog class that inherits from the mammal parent class. The dog class has an attribute called species, and its own method called greet, which prints the string, "Hi, I'm a species," and also prints the output of calling the identify method from its parent's class. Let's see how this works. First, we need to create a dog object, so we'll do that and store it in a variable called dog, and then we call the greet method on the dog object. And remember, the greet method came from the dog class. So first it prints, "Hi, I'm a canine." You may also recall that the greet method in the dog class includes a call to the identify method of the mammal class. And the result of that is what gets printed next. "I'm a mammal." You can see here that we can easily access information from both the dog class and its parent's class, and we can do that through inheritance. Polymorphism is when several classes or subclasses have the same method names, but different implementations for those methods. The classes are polymorphic because they're using a single interface with entities of different types. Let's look at an example. Suppose we have a parent class called shape. Suppose we have a child class called circle that inherits from the parent class. And suppose we also have a child class called square, which also inherits from the shape class. Now, the shape parent class could have a generic method called draw. The circle class would need to override the draw method and provide its own details like the origin of the circle and how big the radius is. Likewise, the square class would need to override the draw method with where you should start drawing the square from and how long the edges are. Let's look at an example in code. Here we have our parent class called shape, and we have a very generic draw method here. I'm going to create a circle class on this side. First, I'm going to import pi from the math module, and then define my class. You can see here that the circle class inherits from the shape class. I'll create an attribute called radius_centimeters and set that to 4. I'll create another attribute called origin and set that to 0, 0, which is a tuple. And now I'm defining my draw method, which is actually overriding the draw method of the shape class that we inherited from. In this draw method, I'm creating a circumference value, pi times r squared, and then I could write some code to draw the circumference at the origin of the circle. You should be prepared to write classes and to create objects in your coding interviews, because again, classes and objects are everywhere in production code, and your hiring managers will want to make sure that you understand these concepts. If you've ever asked someone for advice on what to study for a technical interview, you've probably heard from more than one person that you should study data structures, and it's true. Why should you study data structures? One very big reason is that coding challenges that make use of linear data structures are very common in technical interviews, especially for entry-level roles. The reason is that some interviewers believe a candidate's knowledge of data structures is indicative of the depth of their knowledge about computer science topics. Sometimes a common data structure may be an ideal tool to help solve a problem, whether in a technical interview or in a real product. The most common linear data structures you'll see in a technical interview are stacks, queues, singly linked lists, and doubly linked lists. Stacks are what's called a last-in, first-out data structure. This means that the most recent thing that you put on your stack is going to be the very next thing that you'll have access to. You can think of a stack like a stack of pancakes. You always take the top pancake from the stack, rather than taking the bottom pancake and creating a mess. Because it's so easy to access that top item, you can add and remove items in constant time. Another benefit of stacks is that they maintain items in the order in which they were added. You should use a stack when you want quick access to the most recent item and need to keep the items in order. Queues are pretty similar to stacks, except they're a first-in, first-out data structure. This means that you'll always process items in the order in which they were added. You can think of a queue like a line of people waiting in line to pay at the grocery store. The person at the front of the line is going to get to pay next. You can add items to a queue in constant time, which would be like someone joining the end of the grocery line. But you can only remove items in linear time, which would be like a person waiting their turn in line as everyone else gets to pay before they do. Just like stacks, queues also maintain items in the order in which they're added. So you want to use a queue when you need to process the items in order. To go into much greater detail about stacks, queues, and decks, be sure to check out my other LinkedIn Learning course. Let's shift gears to linked lists. Here you see a singly linked list. It's made of a series of connected nodes, and you can move forward through the connected nodes. That's why you see arrows pointing in only one direction. You can add and remove nodes before or after any key in your linked list. Singly linked lists allow you to maintain the order of the items, depending on when and where you add those new nodes to the list. To figure out whether or not a singly linked list is the right data structure for your particular application, there are a few things you should keep in mind. If you need to store an unknown number of items, a linked list might be a good choice. As long as you're okay with the one-directional movement, a singly linked list would work. It will also allow you to insert items in between other items, which would have impacts on time complexity if you were to use a built-in list. Lastly, as long as you're okay with the sequential access nature of a linked list, it could be suitable. A doubly linked list, as you can see from the arrows, will allow you to move both forwards and backwards through your nodes. So just like a singly linked list, they're made of a series of connected nodes. You can move forward and backward through the nodes, and you can add and remove nodes before or after any key in the linked list. As you can see, they also maintain items in the order that you choose based on when and where you add or remove nodes. You should use a doubly linked list when you need to move forward and backward through the connected nodes. How do you know if a doubly linked list is the right data structure for your use? If you need to store an unknown number of items, if you need to insert items in between other items, and if you're okay with the sequential access nature of the linked list, a doubly linked list could be the right choice. To learn a lot more about linked lists and how to implement them, be sure to check out my other LinkedIn Learning course. I highly encourage you to understand how these linear data structures work so you don't have to memorize their implementations and the code for every single one of them. Let's move on to the nonlinear data structures. Like we discussed with the linear data structures, the reason why we study these is because coding challenges that make use of them are very common in technical interviews. And especially for mid-level roles, these nonlinear data structures come up quite a bit. Again, some interviewers believe that a candidate's knowledge of data structures tells them a lot about the depth of their knowledge about computer science topics. And it could be the case that a common data structure may be an ideal tool to help solve a problem, whether that problem comes up in a technical interview or in a real product you're working on once you get the job. Let's talk about trees, binary search trees, graphs, and hash maps. First up is trees. Trees simulate a hierarchical tree structure with a root node and 0 or 1 or more subtrees. Trees can have parent, child, and sibling nodes. In the diagram you see here, 2 would be the root node, or a parent node. Its child nodes would be 7 and 5, and because 7 and 5 are on the same hierarchical level, we could also call them sibling nodes. Another characteristic of the nodes 7 and 5 is that those nodes themselves are parent nodes to the child nodes that come below them. You want to use a tree when you need to store data hierarchically. Classic examples are a family tree or a predator-prey diagram. A closely related cousin to the tree is the binary search tree. In a binary search tree, the root node is roughly the midpoint. Any smaller nodes go on the left, and any larger nodes go on the right. Here, 8 is the root node, or the parent node, and its child nodes are 3 and 10. 3 appears on the left because it's smaller than 8, and 10 appears on the right because it's larger than 8. And this pattern of smaller on the left, larger on the right, is consistent all the way down to the bottom of the tree. Lookups can be done in a binary search tree in O of log n time. This should sound familiar because we covered this in our chapter on time complexity. You get O of log n time in binary search because every time you eliminate options, you eliminate half of what is left. For example, in this diagram, if we were looking for the number 7, we would first get to the root node, which is 8. We know that one of the rules of binary search trees is that any number smaller than the node you're on is to the left. This means that we can immediately eliminate all of the options that are to the right of number 8. The next node we get to is the 3 node. 7 is greater than 3, so we know that we can immediately eliminate all the options on the left and instead focus on everything that's to the right, and so on and so forth until we eventually get to the number we're looking for. Use a binary search tree when you need to store hierarchical data in a way that is easily and quickly searchable. A graph is a finite set of nodes, sometimes called points, that are connected by lines, which we sometimes call edges. The edges can optionally have their own values. In this diagram, we see that we have nodes lettered A through F. These edges don't have values associated with them, but they could. You should use a graph when you need to store data in a way that captures relationships between nodes. A classic graph example is a social network. When we use a graph to represent a social network, we can see how friends and family members are all connected to each other. Last on our list are hash maps. Hash maps allow us to map keys to values. They use a hash function that computes an index into an array of slots where the desired value can be found. This should sound very familiar because Python dictionaries are effectively hash maps. We start with a key, in this case a list of names, and each of those names gets processed by a hash function. The hash function converts those names into numbers, which you can see here, 1, 2, and 14. Those numbers are sort of like the address of where the value is stored. In this case, the value is phone numbers, which is what you see here in green. You can search, add, and delete inside of hash maps in constant time. Use a hash map when you need to store data based on a key that can be used to retrieve the data later. The obvious example again are Python dictionaries because they allow us to map keys to values. I encourage you to understand how these nonlinear data structures work so you don't have to memorize their implementations. Another common thing that you might be tested on in a technical interview is sorting algorithms. So why should you study sorting algorithms? Getting a question about sorting algorithms in a technical interview is more of an academic exercise meant to test your knowledge of computer science fundamentals. So implementing sorting algorithms can be tricky, as can trying to explain the differences between them. Interviewers want to test your knowledge and communication skills, which is why they ask about this. The reason why you should study sorting algorithms is because coding challenges that make use of them are pretty common, especially for more mid-level roles. Implementing sorting algorithms can be tricky, as can trying to explain the differences between them, so interviewers want to test your knowledge and communication skills. The sorting algorithms we'll cover here are insertion sort, merge sort, quicksort, but there are many more. You don't necessarily have to study all of them, but starting with these 3 will set you up nicely. Insertion sort is a very simple algorithm. It's best used on shorter or almost sorted lists. How it works is it looks at one list element per iteration and grows a sorted output list by placing the element in its correct position in that final list. It sorts everything in place, so memory usage is low, and that's good. But the average runtime is O of n squared. Not so good. So there are better choices. Here's an example of how insertion sort works. You can see that we're starting in the top row with the leftmost element, which is 4. In the second row, we move one element to the right, which is 3. 3 is smaller than 4, so we need to move it to the left of 4 so that when we read from left to right, things are sorted. You can see in row 3 that we've done just that. The item that has 3 in it is now on the left of 4, and now we're looking at the 2. In the fourth row, we have to move the 2 to the left of 3, and you can see how we continue on in this way to keep everything sorted. A better choice than insertion sort is merge sort. Merge sort is efficient, it's general purpose, and it works by comparing items. It breaks down a list into individual elements. It will continually put elements back into sorted pairs until the list is reassembled in order. The memory usage is O of n, or linear, and the average runtime is O of n log n, which is much better than the O of n squared we get with insertion sort. Here's an example of how merge sort works. You can see at the top we start with an unsorted list. We continually break that list down into smaller and smaller chunks until we're left with pairs. And once each pair is sorted, we then begin recombining those pairs until what we get is a final sorted list. Even better still is quicksort. Quicksort is also comparison-based, but it uses the divide and conquer strategy. It chooses something called a pivot in the list. Quicksort moves all of the elements that are smaller than the pivot to the left of the pivot, and all of the elements that are larger than the pivot to the right of the pivot. It recurses and continues to do this until the list is sorted. It sorts everything in place, so memory usage is low, and it also has a pretty good runtime of O of n log n. At the top of this diagram, you see an unsorted list. Highlighted is the number 3, which is the final element in the list. This becomes the pivot. On the second line, you can see that we put 3 in the middle, and all of the items that are less than 3 appear on the left, and all of the items that are greater than 3 appear on the right. Note that at this stage, it doesn't matter if the items on the left and right are sorted yet. You can see that we take the last item on each of those smaller lists and convert it into a pivot too. We now need to process the remaining item, so the 2 goes to the right of -3 because it's larger, and the 9 goes to the right of 5 because it's larger. Finally, we can recombine all of the elements into a sorted list. Understanding the qualities of various sorting algorithms, things like space complexity, time complexity, and whether or not it works best on unsorted, semi-sorted, or almost sorted lists, can help you figure out which algorithm is best to use for a specific problem. I strongly recommend you understand how these sorting algorithms work and how they compare and contrast with one another, so you don't have to memorize the implementations for every single one. Searching algorithms go hand in hand with sorting algorithms. The reason why you should study them for technical interviews is that coding challenges that use them are pretty common, especially for mid-level roles. Knowing how to implement searching algorithms can be tricky, just like sorting algorithms, and explaining the differences between searching algorithms can also be somewhat complex. So interviewers want to test your knowledge about these and your communication skills. The searching algorithms we'll cover here are binary search, breadth-first search of trees, depth-first search of trees, but there are many others that you should probably take a look at. We'll start with binary search. Binary search compares the target value to the middle element in a sorted list. If the target value and the middle element are not equal, the half in which the target value can't exist is eliminated. And this is possible because we start with a sorted list. This midpoint search is performed recursively on the remaining half until the target value is found, or sometimes not found. The worst-case runtime of binary search is O of log n. Let's take a look at a diagram. Here you can see we have a list that is already sorted. The target value we're looking for here is 7. We take this original list and we find the midpoint, which is 14. 7 is less than 14, so we can immediately eliminate everything to the right of 14. This effectively cuts our search area in half. Because binary search is done recursively, we repeat this process until we find or don't find the number 7. So the next step would be to look at the midpoint between the 0th element and the element that has 14 in it. This midpoint is 6. 7 is greater than 6, so we can eliminate that half of what remains. This continues until we eventually find the number 7. Here's a tree example for binary search, which we already covered in our video on nonlinear data structures. Suppose we again want to look for the number 7. We start at the root node, which is 8, and we know that 7 is less than 8. So we can immediately remove all of the options that are to the right of 8. We instead focus on everything that's on the left. So we progress to looking at the node that has 3 in it. 7 is greater than 3, which means it has to appear to the right of 3. We continue on to the node that has 6. 6 is still less than 7, so again we continue on to the right of 6. And we eventually find 7. You should use binary search when you're looking for a node in a binary search tree, or if you're trying to find an element in a list that is already sorted. Breadth-first search is an algorithm for traversing trees and graphs. It starts at the root node and explores all of the sibling nodes before moving on to the next level of siblings. I'll show you an example using a tree. In this tree, Each node contains a number that corresponds to the order in which that node is visited in a breadth-first search. Of course, we start with the root node, which is 1. We then look at every node that's on the level directly below that, so 2, 3, and 4. Then we move a level lower, and then a level lower. This is how breadth-first search works. When should you use breadth-first search? You want to use this if you're finding the shortest path between two nodes in a tree or an unweighted graph. You don't want to use breadth-first search, however, on a graph or a tree with a high branching factor, since all of the current nodes are kept in memory in the implementation for breadth-first search. Depth-first search is slightly different, but it's also an algorithm for traversing trees and graphs. Depth-first search starts at the root node and explores as far down the path as possible until hitting the end. It then backtracks to the node that was the most recent root node and explores downward again. In this diagram, we again start at the root node, which is labeled as 1. We move on to node number 2, and then to 3 and 4. You can see that we don't go layer by layer like we do with breadth-first search. We instead go as far down one path as we can. In this case, when we get to 4, 4 doesn't have any child nodes, so we backtrack to node 3, and then we progress to node 5. 5 also doesn't have any child nodes, so we go back to 3, and then back to 2, and back down to 6, and so on until we've looked at the whole tree. When should you use depth-first search? Use depth-first search if you want to exhaustively explore every possible path. You can also use it if you're looking for the longest path between two nodes, or when backtracking is important for your scenario. However, you don't want to use depth-first search on very deep or infinitely deep graphs. You might hit the max recursion depth before you find what you're looking for. Understanding the logic and strategies employed by various searching algorithms helps you know which is best to use and when. During your coding challenges is when you'll need to put all of these pieces together. I'd like to offer some strategies for staying calm and making sure you can remember everything when you're going through coding challenges. My first piece of advice is to do as many different types of coding challenges as you can. In this case, variety and learning over sheer quantity are much more important. I recommend solving the challenges on your own with a pen and paper or in a non-code text editor. Or if you have access to a whiteboard, that's even better, so that you mirror the environment you'll be in when you're on site. You should talk aloud as you work through the challenge, as you would in a real interview. Believe it or not, talking about code as you're writing it is actually pretty difficult, so the more you practice this, the easier it will become. I've put together what I call a problem-solving framework. This helps me remember each of the little things I need to be thinking about when I go through a coding challenge. The very first thing I do is to write down the main parts of the coding challenge. If I'm whiteboarding, I put this up in the left-hand corner of the whiteboard, or if I'm using a text editor, I'll write these out as comments. I make note of things like, what am I being asked to do? What's the main point of this coding challenge? What are the inputs that I'm being given? What are the outputs I need to send out of my function? I also make sure to ask the interviewer about any assumptions I may be thinking about. Edge cases are also a good thing to keep in mind, and you should feel free to ask your interviewer about those. When I'm doing a coding challenge, I never ever jump straight to the code. I always write down my ideas first. Again, not in code and not even in pseudocode, just plain English, so I can get all my thoughts out. Then I convert those ideas to pseudocode or comments. Finally, after I've written the pseudocode, I can get started with the code itself. I usually find that if my pseudocode is pretty good, the code pretty much writes itself. Once I have code on the whiteboard, I run through the code line by line using a general test case. If that goes well, I run through the code again using one or more edge cases. And of course, I be sure to involve my interviewer at every step of this process. If things check out, then I can move on to finding the runtime of my solution. And I do think it's a good practice to ask your interviewer if there's anything they think you could do to improve the solution or to improve the runtime. This is a good signal to them that you're thinking about constantly improving both yourself and the code. In terms of whiteboarding specific or pair programming specific advice, I would say that you should try not to get flustered if you forget syntax or method names. Most interviewers are going to care way more about your problem-solving ability, your ability to communicate about your code, than they are about curly brackets or whether or not you got the right name for some built-in method on a list. Also, try not to get upset if the problem is too hard or you don't complete it. Sometimes this is intentional. I've been in situations where the interviewer has told me after the fact that they knew the question was too hard for me, but they wanted to see how far I would get. Or maybe they want to see how I do when I get frustrated or if I'm under pressure. Just because you don't finish a problem doesn't necessarily mean that you won't get the job. If you did a great job communicating your thoughts and asking for feedback throughout the process, that goes a long way, so don't be discouraged. It's also okay to ask for help. A lot of people mistakenly believe that it's sort of like a battle, them against the interviewer. But your interviewer really does want to collaborate with you, and so I think it's a good idea to ask them occasionally if you're headed in the right direction. Doing this might save you some time and some frustration. All of these things make up my coding challenge routine. And I think having a coding challenge routine will help you remember important steps and help you stay calm. I'd like to wrap up the course by offering some other advice. These are not technical skills and not comments about personal qualities, but more just general advice. The very first thing would be to start applying for jobs before you feel ready. I know the temptation is really strong to feel like you can't start applying for jobs until you've mastered all the data structures and all the algorithms, but I would really encourage you not to put yourself in that corner. The reason is that failure is inevitable in an interview process. In my opinion, it's better to just get it out of the way and learn from those experiences so you can incorporate that learning into subsequent interviews. Teaching is one of the most effective learning tools, so I'd like to suggest that you find someone you can teach. If you don't have anyone nearby, you can always choose a stuffed animal or a rubber duck. This is where the concept of rubber ducking comes from. But forcing yourself to explain concepts and hear them out loud and hear yourself saying it will really solidify things in your own mind. Failure and rejection are part of the process. It's pretty much impossible to be a perfect candidate. If you get rejected by a company, it doesn't necessarily mean they didn't like you or that they didn't think you were great. It just means that whatever they need is not aligned with what you're able to provide at this point in time. It could be the case that 6 months from now or a year from now, you all are a great match, and that's why you should continue to apply for companies even if they've rejected you in the past. This one has been really important to me. You don't need every company to want to hire you. You only need the right company to want to hire you. Now, the unfortunate part is that you have to get through quite a lot of companies telling you no in order to get to the one who's going to tell you yes. But the company that tells you yes is a very special company, and that's because they see something in you that not a lot of the other companies were able to see. And that is the type of company and the type of people who you want to work with. I really encourage you to take the time to interview your interviewers. You get to control part of this process too. I know sometimes it feels like when you're interviewing that you're just at the mercy of all the hiring managers and you have to go with what they say. And sure, that's true to some extent, but you also have agency in the process too. So take some time to come up with good questions that you want to ask your hiring managers and the interviewers. These questions should be designed to help you get the most useful information about the company and the team as possible. You could also structure your questions in a way that helps you identify red flags. Last but not least, you can do this. It's really hard, it's emotionally draining, but you can do it. A lot of people have done it before you, and you're setting the stage for a lot of people to do it after you. So stick with it. Now that you've seen the programming concepts that appear most frequently in technical interviews, and how to demonstrate your knowledge of them using Python, choose to set aside a small amount of time each day to practice these on your own. To go deeper on the data structures and algorithms we covered, or to learn more about object-oriented programming, I highly recommend these resources. The first is a free interactive book you can read online called Problem Solving with Algorithms and Data Structures Using Python. The next set of resources I recommend are all courses available here in the library. The first two are two of my other courses, one on stacks, queues, and decks, and the other on linked lists. In these courses, I cover these data structures in great detail using Python. The other two courses are called Programming Foundations, Object-Oriented Design, and Python Essential Training, especially Chapter 9 of that course, which deals exclusively with classes. Thank you so much for joining me in this course. I hope what you've learned has increased your confidence and helped you prepare for your next technical interview.